Yo, welcome to another video. Thought I'd try something out besides the hey guys, so yeah. Today's learning objective: solve linear equations in one unknown algebraically, including those with unknown on both sides of the equation, and find approximate solutions using a graph. In terms of prerequisite knowledge, some of the algebra stuff we've covered a few videos back is going to be quite important here. And also just remembering what kind of the definition of equations are. I did kind of a whole video on the definitions of terms like this, so make sure you check that out if you kind of forgotten that. Alright, let's get into it. If you remember, basically an equation is something like, 2x plus 7 is equal to 12. And an equation is only true for certain values of this x. It's not true for every value. And that's just kind of as a quick reminder of what equation is. And when it comes to equations like this, right, there's a big principle in math. Well, actually, let's try solving this first. So if we had maybe perhaps an easier equation than this, say we had something like 2x plus 3 is equal to 7. Well, one way we could solve this is just by kind of guessing what values of x will work, because after all, the equation the value of x we're looking for is the value of x which satisfies this equation, i.e. makes the left-hand side equal to right-hand side. So for example, we can try, x is equal to 0. That could be a case. Well, then we have 2 times 0 plus 3, which is equal to 3, which is not equal to 7. So, x equals 0 is not the solution. How about x equals 1? Well, we can have 2 times 1 plus 3. Well, that is equal to 2 plus 3, which is 5, which does not equal 7. So again, x equals 1 isn't the solution either. Let's try x equals 2. 2 times 2 plus 3, well, that's 4 plus 3, and that is 7. So, the value of x that does satisfy this equation is 2. But you can see how doing this kind of trial and error thing would take ages if we, had kind of a perhaps more complicated equation, or the value wasn't so close to 0, for example. And if I wasn't so lucky to start at 0, if I perhaps started at, say 10, just because I thought maybe the solution is a bit of a larger number. So there is actually a better way of solving an equation than just this trial and error. And it kind of hinges on this principle in mathematics, basically, where if you do something to the left-hand side of the equation, you have to do the same thing to the right-hand side. So for example, if you were to add, say, 5 to both sides, right, if you were to add it to the left-hand side, you have to add it to the right-hand side. If you don't, for example, if you had, say, something like, x plus 1 is equal to 4, right? And then that, clearly, you can guess your x is going to be 3. But if you were to add, say, 1 to the left-hand side, but 2 to the right-hand side, well, x equals 3 no longer satisfies this equation, because 3 plus 1 is 5, which does not equal 4 plus 2, which is 6. So if you want to keep the equation true and keep like the left-hand side equal to the right-hand side, you need to do the same thing to the left as you do to the right. And that's just the principle that we'll use to solve these equations. So let's write it out again. 2x plus 3 is equal to 7. And since we know we can do the same thing to the left and the right, let's write this in a way that's a bit easier for us. And the way we tend to do this is to isolate our x. So we take away 3 from both sides. So let's do minus 3, minus 3. Well, on the left-hand side, we have 2x plus 3 minus 3, which is just 2x. On the right, we have 7 minus 3, which is 4. And now we can divide, if we divide both sides by 2, so we can get the x on its own, right? So we divide by 2, we have 2x over 2, which is 2, is equal to 4 over 2, which is 2. And we've got the solution we had before. And basically what you're doing is the general processes here is just isolating the x as in whatever way we can. So it's almost like reverse BODMAS in this case, because you have, for example, BODMAS, right? So we're starting off with getting rid of this addition, so which is here. And then we go to division. So the multiplication here. So we reverse this addition here. Let me use proper colors. So we reverse the addition here, and then we reverse the multiplication of that. Oh, that's the same color. Okay, it's not letting me change. Okay. Yeah, there we go. So that's the opposite of multiplication. So basically, you see this addition, you do the opposite of that. So you minus 3, And then you kind of do that to both sides, remember. And you see you do the opposite of this multiplication, which is division, to get the x on its own, basically. So let's just work through a few and we can see how that happens. Okay, so actually, let's use the purple for the question. 5m plus 15 is equal to 35. This is very similar to the one we've just done, so I'm going to give it a go and see what happens. I'll just wait here. Okay, I hope you gave that a go. So first thing we're going to do is remember we have to get the m on its own, and so what first thing we're going to do is kind of the opposite of this addition here. So take away 15 to both sides. Take away 15 from both sides. So minus 15, minus 15, and then so we get on the left hand side we get 5m, and on the right we get 20, and then again we divide both sides by 5 because we want to get the m on its own. Remember, because that's how we're solving it, right? We're looking for m. So we need to rearrange it in terms of m, which is kind of, I've talked about this in the video before, so it's the same principle. So 5m divided by 5 is just m, and 20 divided by 5 is 4. And there we go. Let's do another one. Purple again. M plus 12 all over 7 is equal to 23 plus 2m. Okay, now here we've got a bit of a tricky thing because we've got the m on the right and on the left. So we'll have to do something a bit more differently, which we'll see in a second. But the first thing we can do is you can see how annoying this m over 7 is, right? I mean, we can keep it as it is right now, but wouldn't it be nicer if we kind of just had, whole numbers everywhere and no fractions? So if we times both sides by 7, we can get rid of the fraction. So times 7 and then times 7, times the whole thing by 7, of course. So on the left we have m plus 12 over 7 times 7, which is m plus 12. And on the right we have 7 times by 23 plus 2m, which is 7 times 23 is 161, and then 7 times 2 is 14, so 14m, so m plus 12. And now we have m on the left and on the right. And if you remember from our kind of bit on rearranging what's it called, for a certain kind of variable, we want to kind of collect the like terms. So, and we want all the m's on one side and all the numbers on the other side. So what we'll do is we've got 14m here and then m here, right? So if we take away m from both sides, on this left hand side we'll only be left with the 12, which is kind of a step closer to what we want. So if we kind of take away m from both sides, so minus m minus m. So on the left we are left with m plus 12 minus m, which is just 12. On the right, we're left with 161 plus 14m minus m, which is 161 plus 13m. And now on the right-hand side, we've also got this kind of pesky 161. You want to get rid of that. So if we kind of get rid of 161 from both sides. So on the right, we're left with 13m, and on the left, we're left with 12 minus 161, which is minus 149. 149. Ooh. And remember we need the m on its own, so we can divide both sides by 13, and we get m is equal to minus 149 all over 13. I don't think that simplifies. No, yeah, that doesn't simplify. So we can just leave it like that. So again, what we need to do is same as the process of kind of rearranging, as I talked about a few videos ago. Just kind of get all your m's on one side, and all your kind of numbers on the other. And that's kind of all there is to it. You don't kind of have to do these intermediate steps of writing minus m. You can kind of just, as you'll see in the next example, I won't necessarily do these kind of intermediate steps, just so it's a bit quicker, especially once you gain a bit of fluency. It's a lot quicker to do that. Okay, so the next question is 14, let me switch to purple. 14x plus 11 all over 2 is equal to 2x plus 8 all over 3. And again, these fractions are a bit pesky. I don't really like them. What I tend to do is just kind of multiply it up to get rid of them. So if I multiply the left-hand side by both sides by 2, I can get rid of this fraction here. So times the left and right by 2. So the left will just become 14x plus 11, and the right will become 2 times what it was before. So 2x plus 8 all over 3. And again, we can get rid of this pesky fraction here on the right by multiplying both sides by 3. So we have 3 into 14x plus 11, which is equal to 2x plus 8. And like now we just multiply out. 3 times 14 is 30 plus 12, which is, what is that, 42, plus 11 times 3 plus 30, sorry. Let me write this a bit clearer. 42x plus 33 is equal to 2 times 2x, 4x, and then 2 times 8 is 16. Again, let's kind of collect our like terms. So we want to kind of minus 4x from both sides. I'm not going to write minus 4x again, so you can just kind of do this in your head. So you minus 4x from both sides, so this 4x will go away, and you take away the 4x from this left-hand side. So 42 minus 4 is 38, so 38x, plus 33 is equal to 16. And now I have to take away 33 from both sides, so I can have, you know, the 38x on its own. So 38x is equal to 16 minus 33, because I've done the minus here already, and this. So I've done 38x plus 33 minus 33, kind of in invisible writing in my head to both sides. But I kind of avoided writing this step out just because it's quicker not to. But I just thought it would be helpful to illustrate anyways. And then 38x is equal to 16 minus 33, which is minus 17. Ooh. Minus 17. So, and then now we divide both sides by 38 to get x on its own, minus 17 all over 38. And that's it. Sometimes you shouldn't be too afraid if kind of a number is a bit dodgy like this. You know, sometimes the question is just like that. So just if you're worried by getting a slightly weird answer, just you can always use this number. Get your calculator out and plug this back into this original number. So into this original equation and see if it works out. Just as a quick check if you wanted to. Final question, or final kind of algebraic question, is a half x plus a third is equal to a fifth x plus 4 over 7. Again, we've got these pesky fractions here, but you know, if we do multiply out by all these fractions, we might get really big numbers. So in this case, since there's so many fractions, it might be better to kind of stay with fractional form right now, and then we can see what happens. This is just a matter of personal preference. If you really wanted to, you could kind of multiply, you know, the left-hand side by 2, left and right-hand side by 2, and then by 3, then 5, then 7 to get that. But you can see how that's going to be pretty big numbers. So for example, the x term will be 3 times 5 times 7, which is like 35 times 3, which is, what is that, 90 or 105 or something. So, you know, it's going to be a pretty big number in that case. So it might just be easier to kind of deal with a fraction, perhaps. That, again, just personal preference. So first thing I'm going to do is collect the x terms and kind of collect the regular terms in one step now, because as you get more comfortable, you can kind of easily do this in one step. So on what you're going to do is take away minus a fifth x from both sides to kind of get rid of a fifth x on this side, and take away a third from both sides to get rid of this third here. So that way on the left you only have x's, and on the right you only have the kind of numbers. So a half x minus a fifth is equal to 4 over 7 minus a third. Sometimes a bit of a trick here is kind of, you can think of it as taking this term over to this side, but when you take it over this equal sign, kind of this plus sign suddenly becomes a minus. It's just another way of thinking of it. It's perhaps a bit of a kind of a less useful way, because in the sense that you don't see why it's true. But if you wanted to remember it like that, you know, feel free to. So a half x minus a fifth is a half. So we just do a half minus a fifth. So again, common denominator. So half is the same thing as saying 5 over 10 x minus 2 over 10x. And then again on the right hand side, common denominator. So we'll times the kind of top and bottom here by 3, and top and bottom by 7. So 3 times 4 is 12 over 7 times 3, 21, minus 7 times 1, 7 over 21. 5 over 10 minus 2 over 10 is 3 over 10x. And then 7 minus 12, 12 minus 7 is 5 over 21. And then we kind of have to multiply both sides by 10 and then divide by 3. So as you can see, to get the x on its own. So if you want to do this in 2 steps, perhaps you can have 3x is equal to 10 times 5 over 21, and then again divide both sides by 3, which is 10 over 3 times 5 over 21, which I don't think simplifies any later than kind of 50 over 3 times 21, which is 63. And that's our answer. So yeah, that was kind of another one. This was a bit harder because you not only had x on both sides, but you were dealing with fractions. As I said before, kind of you could multiply out all the fractions and then do it, but you know, the way you do it here, doing it this way, you only have to do kind of this multiplying out, you know, on the right and the left with smaller numbers, so it might be a bit easier, but again, personal preference. Now we're going to talk about solving things with graphically. So this question is asking us to plot these lines, and then using the graphs to estimate the solutions to 1 decimal point. I'm going to skip the part about kind of plotting because I feel like, you know, we've covered that in previous videos. I don't really want to sit here see you guys just watch me plotting lines, but you know, remember kind of plotting just 2 points that we need and then just drawing a straight line. So kind of, you know, the y-intercept for A is 4. Would be 4, and then say if x equals 1, it's 4 plus 4, which is 8, and then just getting a ruler and, you know, drawing a straight line through that. If we if I get out the solution, which is just hidden behind this, send back. Okay, here. Here we are. Okay. So this is the kind of the lines plotted. Now we're also somehow use these plotted lines to find the solution to these. And the way to think about this is, right, the equation of a line is this. So let's do question 1, right? So this is asking us to kind of find the solution to, well, on the left hand side is basically, you know, this is A and this is C here, right? And if we think about when we equate them to each other, right, we have 4x plus 4 equals that, right? But you can see if you say y equals that, you can see that this is basically then saying kind of, if we look at the line A, and if we, on the right hand side, if we look at the line C, right, this equates to the line A if we plot it in this form, and this equates to the line C if we plot it. This is asking us, for what value of x is the line kind of A the same as the line C? And another way of saying that is basically, where do the two lines intersect? And that's kind of all there is to it. So all we do is kind of look at where the lines intersect, i.e. have the same value of y for a certain x, and that's it. So we look at A and C. Let's look at A. So this is the line A, the line C is this one here, and they intersect right over here at -1. So we read the x coordinate off, and we can say the answer to this is -1.0 because it's asking us for 1 dp. And just repeat the same principle for each of these. So 4x plus 4, that's line A, and that's line D. So where does A and D intersect? Right over here. So let's zoom in. And kind of draw down. That looks like kind of, you know, maybe -0.2 to me, I think. So I'd say -0.2. And that's already to 1 dp. And then this is line B and line C. So I'll zoom into the graph, and if you can take a minute to pause the video and try this out yourself. So it's zoomed in. So this is line C, this one. This is line B, where's the intersection, and then kind of to find a solution. So this is the intersection, which kind of looks like, what does that look like? I don't know, -0.6 maybe? It'd be a bit clearer on paper than kind of on this laptop screen, so -0.6. Ooh. Sorry. So I'll just write -0.6. I'm not going to bother doing kind of 4 because it's literally the same principle. So when it comes to solving using graphs to solve two equations, the left and the right, what you do is you plot. You have it in the form, you have this. So if you plot the graph of y equals the left hand side and y equals the left hand side and y equals the right hand side, where these two lines intersect, that's where this the x value of where these two lines intersect is the solution for left hand side equals right hand side. Just again to clarify why that is, if we think about this equation of the line y equals left hand side and y equals right hand side, where they intersect, the y value for both is the same, and that's saying then left hand side equals right hand side. So again, if we go back to example A, we've got the line A for y equals 4x plus 4, and the line y equals minus 4x minus 4. Where these two lines intersect, the y value is the same. Look, this is where they intersect. The y value is the same. And that means 4x plus 4 is equal to minus 4x minus 4. So that hence, kind of, the value for x which they intersect is also the value for x which this equation is true. Sometimes if the examiners are feeling a bit kind of a bit trickier and a bit mean, what they might do is actually they'll kind of give you two equations of a straight line, and it won't actually be in the form of the equation you want to solve. It would be kind of, say, if they ask you to solve the equation 1, rather they were asking you to solve the equation ax is equal to minus 8 using the graphs A and C. You might actually struggle to see how you do that, but all you have to do in that case is rearrange to get kind of the left hand side and right hand side into this form, and in this way you'd be kind of taking away 4x from both sides and adding 4 to both sides to get it back into the way it was before. Ooh. So if they're feeling really mean, they might do something like that, but kind of that's a bit less likely. But just as a heads up. So hopefully that all made sense, and kind of there's a bit covered today in terms of solving equations, which is kind of something we've kind of done implicitly so far, and kind of just we've touched upon. But I thought it'd be useful to kind of go over the logic behind it, and a lot of the kind of solving equation relies on you to be able to rearrange the equation so that kind of the variable that's kind of you don't know, so the m, the x, or whatever, is on the left hand side and all the numbers on the right hand side. So just rearranging the equation, it's the same skill. And remember, what you need to do is reverse BODMAS basically. But yeah, hopefully that all made sense, and I'll see you guys in the next video.